my great pleasure this evening to introduce our guest speaker, who will be giving us a talk on quantum computing, Professor Sanders. Before I start, at the end we'll have some questions. I've been told that we need to use the microphones. Hopefully those on your benches are working. And Professor Sanders is the I-Core Chair of the Quantum Information Science and Director of the Institute for Quantum Information Sciences at the University of Calgary. Prof. Sanders also holds a chair in the Kieran Chair in the Division of Quantum Physics and Quantum Information of the Hi-Fi National Laboratory for Physical Sciences at the microscale level at the University of Science and Technology in China. Prof. Sanders received his Bachelor of Science degree from the University of Calgary in 1984 and a diploma of Imperial College supervised by Professor Kibble. He also completed his PhD in 1987 at Imperial College supervised by Professor Sir Peter Knight. His postdoctoral research was supervised by Professor Gerard Milburn at Australian National University and then at the University of Queensland by Professor Crispin Gardner at the University of Waikato. Prof. Sanders joined the physics department at Macquarie University in 1991 and was there for 12 years, including 6 years as head of department before moving to Calgary in 2003. Prof. Sanders is especially known for his seminal contributions to the theories of quantum limited measurements, highly non-classical light, practical quantum cryptography, and optical implementations of quantum information tasks. His current research interests include quantum resources and algorithms, optical and atomic implementations of quantum information tasks and protocols, quantum processes in biological systems, and machine learning for quantum control. It is my great pleasure to now hand over the floor to Professor Sanders, whose public lecture is entitled Whither Quantum Computing. Thank you.
It's a great pleasure to be here. It's my third time in South Africa, my second time to Durban, and I'd like to especially invite Yassira Ismail, who's the president of the newly formed Optical Society of America chapter, who invited me out. And I'm a fellow of the Optical Society of America, and the Optical Society of America runs these programs where those of us we're listed as possible public lecturers, and the Optical Society of America provides all or most of the funding for these kinds of opportunities. And I always find them a great pleasure because I'm actually the guest of the students, not the professors here. It's not so often you get visitors that way, so it's nice. It's also always a great honor to get invited by students. You know, it's nice to know that the students want to hear something you have to say. And I'd also like to thank Francesco Petriccioni and his team. So the funding for my visit comes from the Optical Society of America and from the South African Research Chair Initiative. Down here I put a bunch of logos to try to explain who else I have to thank and what's happening. But over here, Alberta Innovates Technology Futures, the Canadian Institute for Advanced Research, the Canadian Natural Sciences and Engineering Research Council, and AmPrime, which is based, it's a Canadian organization based in Vancouver. Those are the 4 Canadian agencies that have been funding me as I have been working on the stuff I'm going to tell you about. And over here, you can see University of Calgary, which is where I work most of the time. And as you heard in the introduction, I also have a chair in China at the University of Science and Technology of China, where I'm there 10 weeks a year, mostly based in Shanghai, getting very involved as they're building up amazingly fast their capability. And for these 2 months, I'm also a visiting professor at the University of Waterloo in Ontario, Canada. So that's what all those things mean. Okay, and I'm going to tell you about Whither quantum computing, and I'm not sure everybody even knows the word whither. I'm not talking about whither like some tree past its prime, but rather whither in the sense of where's it going. So the point of this talk, I'll give you some background, but I don't want to give you a history lesson on quantum computing. I'll try to give you the idea of what quantum computing is about, but of course I want to end with more about the future, not the past. Okay, so this looks technical. I just put some technical words up so that you can follow what I'm saying, but let me just begin with, the idea here is just to talk about what a computer is. So very funny in the field of quantum computing, because what is a quantum computer? Well, the answer is just a computer. You know, if we manage to make a quantum computer someday, you won't care it's a quantum computer. It'll just be a computer. It might be able to do some things that you can't do otherwise. But the whole field of quantum computing is just about making a computer that can do some things that we don't think will ever be possible if we don't invent a quantum computer. And so probably the hardest part of this lecture is to share with you what a computer is. You know, so you have computers, you use them all the time, but let's try to figure out what is this thing that everybody takes for granted. And so the idea of a computer, as we think about it today, is it's programmable. So you could buy this box, but it will do lots of things. It'll make this presentation. It will solve differential equations. It will do many kinds of different tasks, as long as they can be represented by logical operations or arithmetic operations. So as long as whatever you want to do, even if you're going to do word processing or you're going to play a movie on your computer, as long as we can write it down as a set of zeros and ones, and we can do logic operations, add them, multiply, so if we could do OR operations, AND operations, exclusive OR, things like that, then you can do all kinds of amazing things. So that's how the computer works. It's just a box that has zeros and ones and operations that will take you from one set of zeros and ones to another set of zeros and ones. And then trying to get it to make a pretty image on a screen is really just a matter of transferring these zeros and ones to some way to tell this projector how to project different colors for different pixels. So that's the idea of a computer. And I've put down, it executes an algorithm. So the idea of a computer is, if you want it to do something, ultimately what you tell it to do is written down as an algorithm. And an algorithm has just got three things. One is the input, some string of zeros and ones that you start with. Another is the procedure, which is also a string of zeros and ones. And then there's an output, and that's it. So that's the algorithm. And it's perfectly logical. You know, sometimes we think computers don't do what we tell them, but they always do what we tell them. They're extremely logical. We just sometimes aren't smart enough to tell them the right way. And a computer, and this is very important, the computer is limited in what it can do. So if you buy a cheap computer, you might not have enough memory space or time to play a video game or whatever you want to do, and then you buy more. So the idea of the computer is that we have resources like the memory, like the space, like the time. There might be other subtleties that come in if we parallelize our computers, and then we have communication costs between computers in a distributed network. But the issue for us in computing is, there's two issues. One is, is the task computable? Can it in principle be put on a big enough computer? And the second problem is, will our computer have enough resources to be able to do that? And if it doesn't, then you want to go down to the shop and buy some backups or replace your computer to be able to do the task. Okay, so you get the idea that there are some things that are computable, some things that aren't, and we care here about what's computable, and there's the cost of doing it. And I'll get to more detail later, but the idea of the quantum computer is it makes some tasks affordable. So it means that the cost as you make a bigger and bigger problem goes up slowly, whereas if on a non-quantum computer, I'll call that a classical computer, it might go up fast, exponentially. So the idea is that the quantum computer will make the cost of doing some things not go up exponentially. So if one day we make a quantum computer and you decide to buy one, what you would do is look on a checklist. You'd say, okay, I want to do this, and if I don't buy a quantum computer, it will get expensive too quickly to try to do it. But I buy a quantum computer, and then if I want to play a bigger movie or whatever you're going to do on it, it doesn't get big so quickly. Okay, so that's kind of the idea. And now these notions are laid down in computer science, and there's the famous Church-Turing thesis. Church and Turing were the two independent originators of modern computer science. Turing suggested a Turing machine, and I'll show you in a moment how that works. But the idea that Turing had is that there exists some iconic computer that could simulate every other purpose-built computer. So if you build a computer to do a particular task, you know, to solve an equation, then a Turing machine could also do it where the cost is not much greater. And Church had a more abstract way. He invented what's known as the lambda calculus. This is the basis of object-oriented programming. And so the two of them kind of invented computer science as we think about it from different points of view. So the thesis reflects both their contributions, and it just says something, this is my own wording, but a calculable function, that means it's a function that's suited for a computer, can be, and I put in brackets efficiently, computed on a Turing machine. So the idea is there's a universal computer, and that universal computer could compute anything that a purpose-built computer could do. So if you buy a smartphone and it could do certain things, you could also do it on a Turing machine with with not much extra cost. And the reason I put efficiently question mark in parentheses is that there are two versions of the thesis. One is known as the weak version, and the other is the strong. The weak version doesn't have the word efficiently, and we believe that holds. And it's actually a deep issue here, because if we take all of quantum mechanics and we build a classical computer, is quantum mechanics computable? And we believe the answer is yes. So we believe that everything, even a quantum computer, is computable in the sense of being put on a Turing machine. But there's what's called the strong Church-Turing thesis, and it says efficiently. And so we currently believe that a quantum computer could be computed on a Turing machine, but not computed efficiently. The cost would rise exponentially to do it. So one big thrust going on in the research now is trying to understand and check whether quantum computers are really better. But if a quantum computer is better than a classical computer, then that question mark in parentheses will disappear. Sorry, it won't disappear. It will be false. So putting efficiently down would be wrong. So that's kind of the issue of where a quantum computer is interesting. Do there exist machines that aren't efficiently computable on a Turing machine? And down here, this just makes clear the idea of the problem size and efficiency. So this was done by some computer science students as a project, master's students, who did this beautiful project where they're talking about a Turing machine. And it's nice. So note, I'm going to just pause for a moment. So this is the idea of the Turing machine. The reason I got it, so they did it in Aarhus. Aarhus is in Denmark. Everybody here knows Lego. Lego is made in Denmark. So they use this Mindstorm, which is a way of doing, like, nowadays you don't have to really work with Lego pieces. You can use Mindstorm and just do Lego virtually. So like everything is now a video game, so even Lego can be done on video. So they did this thing. And so this Turing machine that can be used to do any kind of computing, they just devised a Lego, and other people are doing it. So I think at some point we'll even have a Lego-built universal computer, which I think is kind of wonderful. So over here you can see what the tasks are. They show that on this Turing machine it just has to read, it has to write, so it has to read zeros and ones and write zeros and ones. And then over here there will be a tape, you'll see it in a moment, but this Lego device is just going to go around, and the place of the Lego block on that tape is going to be either a 0 or 1. And then what's going to happen is this machine goes down and it reads whether the Lego block is on the left or right. And when it reads it, it then goes through a task which causes, okay, so that's still reading. It's reading 0 or 1. That's a 1. Nothing there, 0. You get the idea. And then it goes along and it writes. And when it writes, it either leaves the block where it is or shifts it to another place. And so the way a Turing machine works is you just have these strings of zeros and ones, and the string of zeros and ones is then able to, it's just called a transition. So you take a string of zeros and ones and just have a step one at a time or two at a time where you change this string. So that's the Turing machine idea. This Lego machine can efficiently simulate any other computer in existence. So one of these days I want to get a Lego kit, and I don't trust these videos, but I'd like to get a Lego kit and try to make it simulatable. Okay, so this is the idea. It's on YouTube, as I said. They don't really sell you an infinite tape, obviously. And Bluetooth. So they're kind of joking about, in their master's project, about what they can do. But I'll stop that. Boom. Okay, so then you have the idea there that, so that's the idea of this Turing machine I talk about, okay? So that's the idea in computer science. Everything can be put on a Turing machine. Okay, now this one, I took this slide comes from Scott Aronson's webpage. So there's a famous blog he writes called Shtetl Optimized, which is the go-to place if you want to really know what's happening in the field of quantum computing. Scott is a computer science professor at MIT, Massachusetts Institute of Technology. And he had a book out last year, Democritus something or another. Anyway, so this is on his webpage. And I just thought I'd put it up here and just try to explain a little bit, because what I want to tell you here is that we have a way now of considering problems we want to put on a computer, and you can imagine that some problems are harder than others. So this P stands for polynomial, and this would refer to the class of all problems that can be efficiently simulated on a Turing machine. Okay? This is the bounded probabilistic polynomial. This is the class of all problems that could be efficiently simulated on a Turing machine if random numbers were free. So if you had a probabilistic Turing machine, then it would be free. But what we believe is that pseudo-random numbers work just as well. So we believe these two classes are actually the same. Now over here we've got NP. NP stands for non-deterministic polynomial. And it's one, I think it's a Clay Prize. It's one of the $1 million prizes. So if you can prove either that these two classes are equal or not equal, you win $1 million. So it's a long-standing problem in computer science. It's the most famous problem in computer science. And this one refers to a class of problems that are hard to solve. The resources grow exponentially to solve it, but it's easy to check. And the question of whether easily checked problems are easy to solve, we just haven't found a way to do it, is a very open problem. And you might not care, except every time you put your credit card number on the internet, your security is based on believing that the encryption you do is based on a problem in that class. So every time that you put private information on the internet to send to a vendor, and you think it's safe, you're believing that this unproven problem is not a problem. You're trusting. Okay? So that's the idea. And one of the key issues is factorization. So if you factorize numbers, it sits there. This one stands for bounded quantum polynomial. This one is the set of all problems that are easily solved on a quantum computer. And we believe that that's bigger than that. So the set of all problems that live in there and not in here make a quantum computer valuable. Okay, those are the class of problems easy to solve on a quantum computer, not easy to solve. And what I told you about the strong Church-Turing hypothesis is if we can prove that a problem in there is not there, then that word efficiently is gone. So that's kind of the theoretical goal. What's interesting, and I'll get more into it, is that every problem that you think makes your credit card number safe on the internet sits in NP. Every one of those problems lives in BQP now. So every problem you use to try to encrypt with what's called a one-way function, that you can encrypt it and believe it's hard to break, but it's easy to check so somebody at the other end can read it, can be broken by a quantum computer. So one reason quantum computing is such an important field now is security. That if a quantum computer can be built, so I'm sorry to tell you that the most important outcome of quantum computer is destruction of e-commerce and the internet as we know it, but this is kind of normal. Like in physics, we like to invent nuclear bombs and things that destroy the internet. So it's kind of normal for a physicist to give you this kind of news. And then up here there are other classes, and I'll just mention this probabilistic polynomial on top is the set of all problems that the computer will get right at least half the time. So if you run it on there, just over half the time it'll give you the right answer, and just under half it'll give you the wrong answer, and that closes those two. But every decision problem from quantum mechanics is in PP. So the PP class covers all of quantum mechanics, those things that we can do efficiently, and then for the physicists here, questions like the gap, energy gap between a ground state and an excited state in a thermodynamic limit would be up in PP. So, okay, so that kind of gives you the idea. And the P space is a set of all problems that can be solved with, say, less than exponential space as the problem increases, but requires exponential time. Okay, so I mentioned about prime factorization, but I thought I'd put it up. So I took this off the web, and it's because I couldn't do it myself. And so it's factorizing the number 72, and through a long, complicated calculation, discovers that it's 2 times 2 times 2 times 3 times 3. Okay, you can probably check this. The point is that factorizing 72 might not look hard here, but as you get bigger and bigger numbers, the resources by the best known algorithm to factorize grow exponentially. So, the idea that we have with security on the internet is we use the hardness of factorization or related problems like discrete logarithm to be able to keep us safe. It's easy to check that that's the answer to the question, what are the factors of 72, but it's hard to find those. So this is the type of problem that a quantum computer makes easy to break. Now, why does this become important? So over here, I'm just going to tell you, and there's actually a large group of people sitting here who are working on quantum cryptography, and so it's relevant to tell you a little about cryptography. So this is the idea of cryptography as we use what's called public key encryption today. So there's what's called an authenticated channel. Bob and Alice talk to each other. Bob knows it's Alice he's talking to. Alice knows it's Bob. But the channel is public, means anybody can listen in. So anybody can read what's going through the channel. And the only thing Alice and Bob know is that they're at least talking to each other. And then Bob wants to send a very secret message, hello Alice, but he doesn't want anybody to break that. It's very important. So he encrypts it. And what he does what Alice does is Alice generates a pair of numbers. She sends one set of string of zeros and ones to Bob, and Bob gets it, and it's public. She can phone him, send it by carrier pigeon, whatever she wants. And then Alice keeps a secret number herself. And Bob takes that number, and he does some sort of addition, binary addition, and that hello Alice becomes a string, which I've written in hexadecimal, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E are the 16 digits. And then when Alice gets it, she decrypts because she takes that, adds it to her number, and gets back the message. So that's the idea of cryptography. The issue is how to get this key out there. So if there's a secret key held by Alice and Bob, they can encrypt and decrypt safely. Sometimes they sacrifice safety for cutting cost, but how to get that key out there? And that's very difficult. So what we do nowadays is we can generate keys online. They're not very safe. They can be broken by a quantum computer. Or we might send a courier, but couriers are either human beings or pigeons, and both can be enticed away from their task. And if you send key and it's stored, storing things, actually a lot of cryptographic breaks are done in the storage phase. So the idea is that what we want to do is to make key live on demand when we need it. You don't want to store it, and you don't want it to be broken. And the reason, so the way it works, and so over here on the left, I've put the RSA algorithm. This is the one that probably everybody is using all the time for any encryption. And this one, what's important here, I won't go into details, but it's on a T-shirt, by the way, so it's funny. You can wear it. Not often you could put an algorithm on a T-shirt and it's easily read. But it says P and Q prime, and then it does some modulo arithmetic. And so the idea there is it's a very simple algorithm to execute, and it involves prime numbers. So this is the RSA algorithm, and this is the one that you can break on a quantum computer easily, and that's the one you're trusting. And on the right, I put elliptic curve cryptography. This is actually done in Canada, so it's Certicom did this, and it's based on something called elliptic curves. It's analytic number theory, if we have any mathematicians here. And so this is type 4 crypto. So in the United States, they have a security agency that rates cryptography. So for the kind of cryptography that we would do, e-commerce, et cetera, they rate it type 4, and we now know from Snowden and the kind of leaks that have come out that agencies in the US can actually read everything you're saying anyway. So these are all breakable. Well, I don't know how breakable they are, but things can be accessed. The type 1 crypto is what is the top standard in the United States for cryptography. And that elliptic curve cryptography is one that's extremely hard to break, and they use that for national security. So when Barack Obama became president the first time around and had his BlackBerry, he wanted to keep using it. They had to put a coprocessor in with type 1 crypto. So they were probably using that. So this elliptic curve cryptography which is really based on polynomial functions and figuring out where they intercept an axis, is also breakable by a quantum computer. So every technique that we know for public key, for distributing the public key mathematically with one-way functions is breakable. So you get the idea that it's extremely important to know what state we're at. So even if we don't have a quantum computer for many years, even developing a quantum computer becomes an important issue to assess national security. Okay, and then the answer, one answer to the problem, which I won't go into here, but I mentioned, is quantum key distribution, which is a big effort going on here at the University of KwaZulu-Natal. And down here I've got an old picture of a D-Day Quantique system, and I saw one today in the labs. And the idea is that Alice is using a box, and Bob's using a box, and there's some coiled fiber in between. And then by running this system, instead of relying on a one-way function to generate key, you just send photons through the pulse, photon pulses through the system, and then Alice and Bob are able to generate a key. And it's not done by mathematics, it's done by quantum physics. And quantum physics, if things are done properly, will guarantee the security against any computational attack. Okay, so then what I want to go to now is to give you an idea of where the quantum computer can be used besides being used for breaking numbers. And so this I put up, okay, so I'm sure almost everybody here knows the matrix, right? If I asked, what is the matrix, you know the answer now, right? Anybody know? Yes. So the matrix, so the idea of the what is the matrix, it was a comic book, What is the Matrix, became a movie. And the idea of it is that we humans think we live in the real world, but we actually live in a simulated world. So our world is really computers that are just sapping our life energy out of us and feeding us neural inputs that make us think we live in the real world. And then there's certain glitches. So déjà vu and the idea that most meat tastes like chicken, these are the glitches that indicate that we're living there. But the idea in computing is if it's within some small epsilon error, it's good enough. So if the computers can run the system and just have these occasional glitches, it's not enough for us human beings to notice that we don't live in the real world. So it sounds funny, but it's actually a very interesting problem. And the problem is, is the world really simulatable at the level that we exist and feel by a computer? Okay, so you understand the question. Like, you know, it becomes an interesting question to say, is nature and the physics of nature really, even in principle, achievable by putting a bunch of computers together? And that kind of question is one that Richard Feynman, who was a Nobel laureate in physics, posed. And so from the late 1950s to until he died in the late 80s, he was on the side, he was thinking about this issue. So he did a lot of fantastic physics. Obviously, if he got a Nobel Prize, one thing that wasn't so appreciated back then, but was quite prescient, is this question. And so I've got a quote up here. He gave a talk in 1981. It's considered to be the seminal talk of quantum computing. And the article is really great. He was giving a talk, and somebody took notes. And so the notes are published in the International Journal of Theoretical Physics from 1982. This quote is taken out of section 5, but I thought I would just read it to you to give an idea. So when I use the Q with the funny font, that's quantum, and C is classical. So he's saying, can a quantum system be probabilistically simulated by a quantum universal computer? So he's saying, let's forget about the Turing machine. Let's ask about a quantum version of a Turing machine. So he doesn't imagine exactly what it is, but he does spell out in a previous section roughly how it would work. He got the concept right. So he's really saying the universe is quantum. And I don't have time here to explain quantum physics, but you kind of Google it after if you're not so comfortable with the word. But he's saying, you know, the universe is quantum. Could it be simulated on a quantum universal computer? So could we, and think about it like the matrix, right? You know, if we live in our universe, we think we live in the universe, but we live in this matrix, is there a way to tell? Well, if it's quantum computers, they would simulate everything we live in, including the quantum aspect of nature. And then he's saying here, he's saying a computer which will give the same probabilities as the quantum system does, so that's technical. If you take the computer to be the classical kind I've described so far, not the quantum one. So the classical one is that Lego Turing machine you saw. So what Feynman suggests here is that a Turing machine could not efficiently simulate the quantum world, and a quantum computer could. And he's quite certain. He says the answer is certainly no. 30 years later, the only thing we're certain of is you can't be certain. So it turns out that now that we've translated it to computer science, and I told you about the $1 million question, this would be a $1 billion question. So maybe Feynman knew it, but we can't reproduce what he was thinking if it's correct. He gives a reason. The reason probably is not valid in this case. But the key point is he was thinking back then about this issue. So the reason I bring up the Matrix, the movie The Matrix, is it's one way to think about it. Just start thinking about the question that, can you put the universe, including all quantum experiments, on a computer to simulate? And so one of the things I like to think about in my crazier moments is why we do quantum experiments, we test Bell inequalities, various things we do, and I always think, okay, the reason we're doing it is we're checking whether we live in the matrix, and it's classically simulated. So I get excited suddenly about foundational physics questions because I think, okay, now I'm going to know if I live in the matrix or not. So that's it. But you don't need to get as obsessed as I am. It's just interesting. Okay, and then this kind of gives you an idea of what a quantum computer does. So this picture, what I want to say to you is I told you at the beginning that a classical computer is really just about strings of zeros and ones and how they change from step to step. That's what a computer does. This is showing in some way that the quantum computer is much more complicated. The first thing is we don't have zeros and ones. The second thing is we don't have the kind of operations. So all I wanted to put down here is to tell you that this box represents our real world. This box represents our quantum computer, and the whole game has changed. So if you like to do fancy schmancy mathematics, it's then a lot of fun because instead of working with zeros and ones and simple transformations, we're suddenly working in these spaces with complex analysis, all the kind of mathematics you have to study for years to get a hang of. And then because it's so hard, it becomes kind of interesting. So over here, the idea is this could be our state now. This could be the state we're in 10 minutes from now. This describes how it changes with t as the time. And then over here, we have to break it up into a set of discrete steps. And then our quantum computer gives an answer on some string of quantum zeros and ones, and I'll explain that more in a moment. And then, remember what I said about glitches and getting things wrong? So computer, if you write a good program, it doesn't always deliver the correct answer. It's just close enough. And so over here, our quantum computer delivers an answer, but what tells us it's close is not the difference between the correct and the incorrect answer. It's some distance in some abstract space representing the computation. So things get a bit complicated. Now let's turn it back and get away from complication. Here, I wanted to point out something. So I mentioned about simulating the quantum world, factorizing numbers. And this, I wanted to give you one more reason a quantum computer is important before we get to how a quantum computer is built. And so this one I put up. This is the famous AX equals B, right? So with kids in primary school, probably grade 4 or something, they start having to solve for x. The frustrating part when you, instead of adding numbers together, there's something written down, and it's what is x, and it drives a lot of people crazy. What is this x? And so this is kind of a little bit more complicated, where instead of solving for x, we write a matrix, not the same matrix as the one we live in. And then the vector and the vector, and then you have to solve all the x's. And it turns out that this is considered a hard problem, surprisingly. And so one beautiful work that came out in 2009 is the idea that that if you look at the complexity of solving this problem, as you make this vector longer and longer, it becomes exponentially difficult to solve some function of those x's. But if you put it on a quantum computer and certain properties are met by that matrix, it can become easy to solve. So one of the beautiful things that have come out in the last few years is the realization that if we can make a quantum computer to solve quantum systems, and quantum systems are described by a differential equation of a certain type, then forget about quantum physics. Just start dealing with all these kinds of equations. And if we take a differential equation, we can convert it to algebraic by finding some basis, I know that's technical, and turn it to an algebra problem. So quantum computers might actually turn out to be useful not just to check whether we live in the matrix, and not just to be able to break into credit card numbers and steal people's money, but it might actually turn out to be nice in that we can solve problems like this. And if we can solve problems like this, these kinds of equations come up if you want to beat the stock market, if you want in a moment when it's in a linear regime, if you want to deal with weather prediction. I mean, linear equations pop up in all kinds of places. So there are ideas. People are still looking for algorithms, but there are good reasons to think about quantum computing. So let's talk about how to build it. Now this looks a bit mathematical, but I told you before a quantum computer doesn't have zeros and ones. I'd be remiss if I didn't tell you what it did use. So over here you can see this 0 with a funny bracket. This is called a ket. And another bracket. So instead of writing 0 and 1, we put some funny brackets around it, and then we think of it as a quantum 0 and a quantum 1. And then the idea is that we can start doing linear algebra to map these. But the idea of the quantum computer is that we have funny zeros and ones, and I'll show you how they work. And then we have ways of mapping it. So just like we had a string of zeros and ones, we can carry the string to new zeros and ones. They're a quantum version. We can prepare in all zeros, and we can read. That's kind of all we need to do to build a quantum computer. And then we need 3 operations. So just like on that Lego Turing machine, you could see that zeros were mapped to ones or to zeros. In order to map our zeros and ones, we just have to build devices that will affect 3 different kinds of transformations. So now I'm going to take you to a circuit and explain to you what it means. So in building a quantum computer, all we have to do is build 3 kinds of operations. So this makes it experimentally feasible. We don't have to build some very, very complicated device. All we need to do is to build 3 operations in the lab and be able to put them together, and we can make a computer. This is like a regular computer. You have transistors, so you might want to do AND operations, not. Basically, if you can build transistors and put them together, you could build a computer. So this is the quantum version of building transistors. 3 things we have to make. And that H takes a 0 or 1 into a superposition, a coexistence of both 0 and 1. R does it as well in a different way. And this one says if one bit is 0, don't change the other one. If one bit is 1, do change the other one. Now I want to explain these, but the way I'll do it is if a quantum computer can simulate anything, then it can simulate Schrödinger's cat. Now, I don't know if you know Schrödinger's cat. It's kind of the most famous example in all the popular quantum mechanics textbooks. So what happened was Schrödinger was one of the originators of quantum mechanics in the very early days. And in the 1920s, Schrödinger, who was one of the originators, decided that his quantum theory was crazy. And he and Einstein and a number of others felt that quantum mechanics somehow had to be wrong. And they constructed various paradoxes. So let's go through the paradox that Schrödinger constructed, and then I'll explain the quantum computer simulation. And that'll explain the gates. So over here in this picture, there's a cat in a box. And in the typical physics cruel way, the poor cat is in a box with a poison gas. And the poison gas is triggered by a nuclear decay. So there's one radioactive nucleus in the box with the cat. And it's an alpha particle decay. An alpha particle is really just a helium nucleus. And in one of the nuclear models, you could think of alpha particle decay as a helium nucleus bouncing around inside like a fluid. And then it hits the wall over and over, and at some time it can quantum tunnel through. So this is the nucleus before decay. That's the nucleus after decay. So the idea is that if the nucleus decays, it causes the poison gas to come out, and the gas kills the cat. If it doesn't come out, the cat's alive. The problem is that quantum mechanics says clearly that you can't talk about these as 2 distinct realities. The nucleus, with or without the alpha particle inside, exist in a superposition. So if you write down your nuclear physics equations, you'll say this alpha particle is in a superposition of decayed and not decayed. It is not what we normally say, that it's either this or that element, right? It's in a superposition of 2 elements. And therefore, if it's tied with killing the cat, releasing the gas, then what happens is if the alpha particle comes out, it triggers gas that kills the cat. And here's what happens. And I wrote these in these funny brackets again. So this is the undecayed nucleus and the live cat, and this is the decayed nucleus and the dead cat. And so what quantum mechanics seems to tell us is that the best description we have of the state of this cat is we have a superposition of undecayed nucleus in a live cat, decayed nucleus in a dead cat. And this disturbed Schrödinger greatly, because the idea that even life and death are not well posed in quantum mechanics is a very disturbing thought, if you're alive. If you're not alive, maybe it's kind of a nice thought to have, I don't know. So then this is the idea. So now I'm going to go back a couple of slides, and let's see what those gates mean. So I introduced those gates for you. Now I'm going to explain what they are. So the 0 and the 1 above correspond to the state of the nucleus. So if the nucleus hasn't decayed, that's now our logical 0. If the nucleus decayed, that's our logical 1, you see? So this is the 0 state, this is the 1 state. The cat alive is a 0 state, the cat dead is a 1 state. If we wait the half-life, so if you take the nucleus and you wait long enough that it's equally probable to decay or not decay, that's that H gate. So we can make that H gate just by waiting a half-life of the nucleus. So I'm being careful because half-life has a 1 over E. So I'm saying about a half-life, but for technical people, you know what I mean. And then that controlled NOT gate is this process here. So what's happening is if it doesn't decay, it says don't flip. What's a flip? If you flip the cat state, you kill it. Fortunately, you can flip it again and bring it back to life. So so that gate is what we call a controlled NOT. It's an XOR operation in computer science. And so the idea here is that turns it into 0, 0 plus 1, 1, which is undecayed nucleus, live cat, decayed nucleus, dead cat. So that's kind of showing you how we do things. So we can, and it's very interesting, we can now take a lot of physics, convert them to what I call algorithmic simulation, and so we can now think of how to put things on a computer. That's why the matrix idea is so interesting, is we can transfer notions of reality and represent them digitally. Okay, so that's the Schrödinger cat paradox. This is a technical slide, but it's just a reminder to tell you that what happened was the quantum computer idea surfaced in the 80s, and what happened is if you look through the literature, nothing happened until the mid-90s. And then the idea is, why didn't it happen? Why was the quantum computer conceived in the early 80s, and then it took about 13 years before papers start to come out? Well, if you're one of the poor saps like I am, who worked on it before the mid-90s, you know the answer. And the answer was I started working on quantum computing in the late 80s, and no paper would ever get accepted. So when you worked in this area, you had to be ready for rejection, get a thick skin. And the reason was because quantum mechanics is fragile. So quantum mechanics tells us how nature works at the atomic level, nuclear, atomic, and molecular level. So if you're not a physicist or work on molecular chemistry, you can forget about quantum mechanics. It's not important to you. And so this reason was why quantum computing was considered to be irrelevant and not publishable in any reasonable journal. And this was a big problem. And there was a champion of this. Rolf Landauer worked at IBM. Landauer was one of the greats in thermodynamics. And Landauer was a great pontificator about how crazy quantum computing was. And the answer was always the following. It's very fragile. Any perturbation to the system, for those people, I know there's a big group working on open systems. Any open system effects would destroy it. And the answer came out by Peter Shor. Peter Shor was at Bell Labs at the time. He's now at MIT in mathematics. And so Peter realized early, he was the guy that figured out quantum computers could factorize efficiently, and he also figured out how to protect. I won't go into the details here, but the idea is the following. Suppose that this room were really noisy, and I wanted to send you a message. And you now know that the only messages I send you are all zeros and ones, right? So we can speak in binary. So if I wanted to send you the message 010, and it's a noisy room, you might miss hearing something. But I could do a redundant encoding. So instead of saying 0, 1, 0, I would say 0, 0, 0, 1, 1, 1, 0, 0, 0. But if you miss one, you're okay, because you know it came in triples. So if you hear the three, if you hear like 1, blah, 1, you know you heard two ones, it's good enough to count as a 1. So one of the tricks in information theory, in computer science, is to overcome noise by using a redundant code. And Peter Shor realized that he could use the same technique in quantum computing, use a redundant code. And the idea is that instead of quantum mechanics being so fragile, it falls off exponentially fast. Instead, if you first code it and then work on the code in your computer and decode it, like we do in a classical computer, you can preserve it. So it's kind of a straightforward idea, but I know I was trying these ideas for years, and I didn't have it. Nobody I knew had it, so therefore I know it's a brilliant idea. It's obvious now, but it's a brilliant idea because I remember nobody else ever thought of this. So you get the idea then. Now, it means that nature is still pleased that quantum mechanics is so fragile, so we can ignore quantum mechanics at the large level. But it also tells us that quantum mechanics can be built up. So we are able, in principle, to make quantum mechanics work beyond a molecular scale. If we realize that we're not working with physical systems, we're working with information systems, and we protect them. Oops. Okay, so now let's talk about how to build a quantum computer. And so the natural question you would ask is, what's it going to look like? You know, it's the tactile way to get into it. So over here, I just want to turn the clock back, say, pre-Second World War. And if you ask the question, you say, well, I know that you can make a computer. What's it going to look like? And so even this question was difficult. In the Second World War, when they were building giant computers to figure out how to do implosions for nuclear bombs, they were using vacuum tubes. Probably most people in this room haven't even seen a vacuum tube, or no one knows what it is. Very funny. Okay, so vacuum tubes are, you've got wires there, it's inside of a glass, and it's got a vacuum just like an incandescent bulb. That was what happened. And then part of the error correction is human beings would run along, and every time a vacuum tube would blow out, they'd have to pull it out and put another one in. So computers were very labor intensive. It gave jobs to people. And then gradually the idea of a transistor came along, and the transistor, with the idea that you can use a current to control and make switches, came along. But the first usable transistors were made of germanium, not of silicon. And then they became silicon. So if you were trying to prognosticate, tell the future, you wouldn't be able to do it then. You know, the silicon transistor came along, but it was not predictable at all. So we're kind of at this stage. We don't know which technique will work, if any. So we're trying them all at once. So there are groups all over the world trying to make quantum computers every which way they can. And so far, almost any way you can think of that looks reasonable, you can get funding for, because we have no idea which one is going to work, if any. So here's one example. And this one is nuclear magnetic resonance. It was the first one proposed, and it was the first one demonstrated. So the number 15 was factorized at IBM Almaden in California by Isaac Chuang. He's now at MIT. You can see MIT gets a lot of these people. And they factorized the number 15. And the idea of nuclear magnetic resonance, it's using the same technology used for brain scans. So instead, you just take a long organic molecule. So it's got carbons, and then it's got other things like chlorine hanging on. And the nuclei have spins. So the idea is that you encode your quantum information into the spins of the nucleus, hit it with some magnetic pulses. So there's a DC and an AC magnetic field, and then you are able to manipulate and get an answer. And this uses the same technology that is developed for hospitals. So it's well developed. The pulse sequences that people are developing in this field are also now having ramifications for other applications. Another technique that's very popular at the moment and is considered one of the two winners is one of the two winning technologies at the moment is trapped ions. And over here, and in South Africa, you've got Herman Uys. Where's he at? CSIRO, yeah. So he's been involved in this. So I know in South Africa, there's an effort to build up this capability. And so this is the idea. You just have electrodes over here that control electric fields. These glowing blue things are ions. They sit in different regions, and they're just going through those gate operations. And the gate operations are done by laser pulses. So you have these ions, they're just charged atoms, and then you just push the electron up or down in energy with laser pulses, and that's your quantum computer. And then over here, these are memories and operation regions. So there's that one. And this one I'm going to talk a little bit about. This is a picture out of Bruce Kane's Nature article, 1998, where he proposed doing a quantum computer which would use silicon with phosphorus. So the idea is you put phosphorus into silicon, and the phosphorus nuclei would be the zeros or ones, the spin of the phosphorus. And that technique really opened the doors to lots of activity, because the concept had come up that maybe we can build this quantum computer and leverage off the whatever $100 billion silicon industry. So silicon foundries exist in the world, they cost a fortune, and the idea that we could combine this with silicon makes the idea of hybridizing a quantum computer with silicon machines possible, and also leveraging off the capability. There's a funding agency in the US that needed to make an argument to continue funding quantum computing at a very high level, tens of millions of dollars a year. And I heard about the problem. And so the problem is the following. You know, sometimes when you get into the very big money, you have a very short time to make a pitch. So the problem was something like, the problem that I was looking at was, how do you make a pitch for $50 million in 10 minutes to people who don't know your field? So that was the issue. So I talked to them and I said, hey, why don't you give me $50,000 and I'll make a movie and that will help. And the movie would be 3 minutes long. This became 4 minutes long. And so I'll show you it. I worked with people in Australia, University of New South Wales and Melbourne, at the University of Waterloo. And the funding came from the US Army Research Office. It's all credited in here. And so the idea was to try to explain how a quantum computer would work in silicon. So let me play, and I'll pause it as I go. Okay, so the idea here, oh, that's great. Okay, I need it because parts of it you need to see features that haven't got great contrast. So the idea is to motivate the quantum computer and to explain that it's a security issue that can factorize numbers very quickly. So over here, what you see is this would be a regular computer, and over there, this is the quantum chip. Some people might know that number. If you don't, it's okay. And then we're diving in, and then we get down to the level where we have phosphorus atoms lying along grid lines and a bunch of electronics living inside. And over here, I'll just pause to explain this step. This is a phosphorus atom with the electron going around it. That's the electron cloud, like you see in chemistry. And over here, these yellow things are the silicon lattice structure all around it. And then what happens, we're just rotating around. And over here, oops, darn, I keep hitting the wrong one. Okay, so we dive in. Each blue dot is a phosphorus with an electron around it. And then, yeah, so there's the phosphorus with the electron cloud. And the electron has spin. It can spin up or down. And that thing that looks like a moon represents the electron spin state. And now here, this is why I needed the dark room. If it's not dark, you can't see those lines. So over here, this just represents a magnetic field that comes in. And it means if the electron is spin up or down, it will have a different energy level. And so that glob that's sinking to the south pole of the moon represents that all electrons are going to be spin down, which is the zero state. And then we apply an AC magnetic field. Oh, sorry. Yeah, so this is the electron spinning. And then over here, there's an AC magnetic field where it's spinning around. And what we're going to do now is change what's called the hyperfine splitting. So it turns out that the precession of the electron going around depends on how much it overlaps with the nucleus. So the idea here is to apply an electric field. We'll see in a moment. This represents the timing. So when you see the flash of light, that's when it's in the one state. So there's a control. Now there's an electrode that'll appear up here. There it is. There's the blue lines represent electric field. It changes the electron cloud around the atom, changes the overlap with the nucleus, and then you're able to control. And so what you see in that moon is a way of controlling the electron spin so we can change it from up to down to some superposition of up and down. So that becomes one binary digit, one bit in our quantum computer, and we're using this electrode and electric fields to control. And then over here, I told you there were only 3 operations we need to do. 2 of them were just operating on 1 bit. This is an operation on 2 bits, where we're using the fact that 2 electrons on 2 atoms have Coulomb repulsion. They repel each other. Okay, so this is just a set of operations to do with 2 bits. So the idea is to demonstrate that there's a capability of doing both 1 and 2-bit operations on the quantum computer. And now over here, we have to have the way of preparing the state, and we have to have a way of reading it. And this sequence here, I won't go into the technical details, is showing how we can read whether a single electron on a single phosphorus atom is in a state 1 or 0. Now, remember what I said about error correction? So we have to put things in a code space. So what you saw was a 2-bit operation, and then that 2-bit operation needs to be put in a code space to keep it safe. Otherwise, it's going to get damaged. So over here, to put it in a code space, we have to do 14, 28, 56 bits. Is that right? I think 57, 14, no, 28. 28 bits and 46 operations. We actually did this for the movie to show the sequence of steps required to put quantum information into code and protect it. And then we had to delay the movie for a few months because the people who designed the sequence liked it and they patented it. So this sequence you're seeing was first patented and then put in the movie. And this is showing all the complicated operations. So this is just an exclusive OR. Remember the operation I told you with Schrödinger's cat? The gas, there's no decay in the gas, alive, decay in the cat's dead. This is the set of complicated operations just to do that step on a quantum computer to overcome the fragility of quantum mechanics. So that was the operation. Now when you pull back, you understand those blue dots on the lines. That's what's going on at a microscopic level. And now with a quantum computer, to break a 2048-bit number, it would take, on average, 4 guesses. So here you see 4 guesses coming out of the quantum computer, and then 1 is being sent over to a classical computer to see it, and the movie has a happy ending. It literally cracks the code, and so we're all very happy. The quantum computer breaks the code, and I think the money came through. So there's a company in Canada based in Vancouver, Greater Vancouver area, and they are selling a quantum computer. They sell what they call a quantum computer. And so they've sold, the first one was to Lockheed Martin. They've sold 3 to Lockheed Martin that I know of, roughly $10 million each. And then they've sold, Google is buying one. Google's been leasing, and Google is buying one. NASA's looking at it. So there's this, D-Wave is a quantum computer company selling a machine, and they're selling them at $10 million a pop, and people are buying them. So the issue then, and the question I often get, it's in the news a lot, it's a big deal. It was on the cover of Time magazine a few weeks ago. So the very cover of Time magazine was on quantum computer. So then I thought I would play you the blurb that this I downloaded from their promotional website. So it's, if you Google D-Wave, you'll see it. This is the D-Wave idea of a quantum computer. It's based on a superconducting technology. Actually, I know I didn't. It's got good background music. Anyway, it's showing you the way they build it. So they just put these superconducting circuits together in a giant grid. And then the idea here, they're going to play it slowly. And so the idea here is they have this quantum bit over here. That's a Josephson junction for people who know it. That's niobium. And then they kind of build this quantum bit to have controllability, variable junction thickness. So this is showing how they build one quantum bit in their quantum computer. And there it is. They now have a magnetically tunable junction, so they can tune them to make sure all the quantum bits are in resonance with each other. They add some various electronics, so there's a lot of electrical engineering or electronic engineering specifically that goes on in the system, and they're going through it. So they build this idea of a quantum computer and they sell it. And then the question is this, people want to know, is this a quantum computer? What are you paying $10 million for? And so this computer is specifically designed to optimize a particular kind of problem. When they optimize this problem, the value of it is pattern recognition. So why would an aircraft company, NASA, Google, with the Google glasses, why would they be interested in this machine? And the answer is they're interested in this superconducting machine because they're interested in ways to be able to do pattern matching, right? You could think of it for security reasons again. You know, if you have an airport with a scanner and you want to do facial recognition, you want real-time recognition of patterns to map it against a database. If you're doing aerial flights, you have to do that. So the idea is that this computer is specifically designed to do an optimization problem where the major commercial value would be in pattern recognition. That's the idea. Remember what I told you at the beginning? I did that class of problems, and I said what makes a quantum computer valuable is that a problem would live in BQP. I had that chart. The problem they're doing is not in BQP. So there's a lot of controversy about this kind of computer because there are people who believe that this will speed up certain kinds of computation and it would make pattern recognition easy. And there are other people like me who believe that a problem not in BQP is not interesting. And there's a lot of work going on and a lot of debate taking place, and you could read blogs about this too, it's kind of the best way to get it, that are dealing with whether this has value for money. So I'm not so, I don't see it as delivering the kind of punch that we want, but there are companies putting up $10 million a pop for the computer. Who are you going to believe? The scientists standing in front of you or companies that are paying $10 million? And so if anybody wants to talk about the details and what's going on, I can do it offline, but I don't want to talk about it with a videotape going. Okay, so I think I'll wrap up. And the wrapping up, I'll just tell you, I wanted to add that quantum information has inspired other ways of thinking. One of them is, so the idea of using quantum computing isn't just making a quantum computer, it's helping us think differently about different things in the world. And so this one tells you about an area of quantum biology. So I met with 3 of Francesco's students today who are working in this general area. And this kind of gives you a rough idea of the problems that have now been classified under quantum biology. The upper left one was Schrödinger. I mentioned Schrödinger at the beginning, originator of quantum mechanics. He wrote a book called What is Life back in the 1940s and postulated that in DNA, which you see there, genetic mutation was driven by quantum processes. It was a very good hypothesis at the time, and it was quickly defeated. But the hypothesis was good to make, and then it was realized that it was not a quantum process, but it's still good quantum biology to make that proposition. Another one is there's a picture of a bird, and so there exists a kind of bird that is able to travel north-south, so it knows the world's magnetic field. Unfortunately, it doesn't know which way north is. So there's this puzzle. How come this bird is flying around? What kind of magnet does it carry, magnetic dipole or magnet, that knows north and south but doesn't know which is which? And so the hypothesis is there exists this mysterious entanglement going on in the system, and the entanglement seems to be the best explanation for how this magnetic dipole works. So there's that's an area of research, including here at this university. Then over here, this kind of represents, and this discussion came up today in one of the groups, in one of the discussions I had, and this is an idea that's championed by Stuart Hameroff at Arizona State University, Roger Penrose at Oxford University, and the idea that it plays on the quantum consciousness idea. I'm not so much into this, but it goes back to Wolfgang Pauli, who was trying to understand quantum mechanics, and the idea is somehow consciousness is we often use the term when the rubber hits the road. I don't know if you know this term. So when the rubber hits the road, when quantum meets classical, from Wolfgang Pauli, there's the argument that consciousness is the dividing line, and over here, there's an idea of a synapse. This kind of represents that there are even more exotic ideas about quantumness and thinking. And over here, this is kind of the big thing in the field, which is photosynthesis. It turns out that there's a kind of bacteria that lives deep in the water where photons, they don't get enough photons. And so there's a complex here. Photosynthesis creates some sort of energy transport by what's called excitons. They travel through the system, and the usual explanation of a diffusive process fails. And so it seems like there's some quantum process going on, sometimes talked about as a quantum walk. So there's these areas and more cropping up. I do a little bit in this area, but none of these. And so that's one direction that things are going. So I'm just trying to give you the idea that quantum computing is interesting in how it's inspiring new thinking in other areas. I wanted to put up Seth Lloyd's book. So the book is here. I don't make any money out of this, so I'm not promoting. I don't get commission. You can buy it or not. It's up to you. And so Seth Lloyd wrote this book called Programming the Universe. Underneath it says, a quantum computer scientist takes on the cosmos. And he argues that the entire universe is a quantum computer. So then the idea is that, what are we doing? We've already have the quantum computer. And he argues by thinking of cosmology in quantum computing terms, it answers a lot of questions. You can read his book. I don't have time to tell you anything about it. Okay, and I told you that Feynman started the field of quantum computing. So I thought I would finish. This is the last slide. And I don't see, nobody's asleep. It's amazing. So, so then with Feynman, he said something very interesting I think a lot about. This goes back to the 50s. But in theoretical physics, we often care, the mantra we have is, let's find the equation for everything. There's the TOEs, theories of everything. And the idea is that there's the universe, and there's some big equation out there that we would look for that would describe everything. And it could be right, but who knows. But Feynman was a maverick thinker. And so one of the things he says, I hypothesize that ultimately physics will not require a mathematical statement, that in the end the machinery will be revealed and the laws will turn out to be simple, like the checkerboard with all its apparent complexities. Checkers, drafts, that. So if you play that game, the rules are very simple, but the patterns can be complicated. And if you go to a more complex version like Go, if you know Go, then there's more complicated versions that come out. They become a very simple set of rules, very complex, beyond human ken. So the idea, when you mix with this notion of the universe as a quantum computer and put that in, the sense that I get from what Feynman was saying is maybe we should think of the universe differently. Instead of trying to find the equation that describes everything, maybe what we should do is to understand the computer as a machine, like a computer, and write down the operations that take place. How does the universe work? Just write down the operations and then regard it as some sequence of transitions in the sense of a Turing machine or its quantum counterpart. So I think this is one of the biggest gifts of quantum computing, is a whole new way to think about the universe. Thanks.